All right, folks. Hey, for those of you that missed today, we're going to get right into the algebra lesson for today, which deals with scatter plots and lines of best fit. Now, if you're a sophomore, you probably know a lot more about this than the freshman because this is more of a physical science idea. And so those of you, we're going to introduce it to you now, but you'll again see it again when you get into your physical science classes. So the first term, bivariate data, I like to break down terms that make more sense to myself when I explain them. And so the prefix bi, we obviously means two, but variate looks like variable. So if you think of it as two variable data, it makes a lot more sense when it comes to the actual definition here. Data that consists of pairs of values, okay? So we have two variable data, an x and a y value, and so data that consists of the pairs of values. Now, I said see bottom of page, so if you look at the bottom of the page, you have weight in pounds versus height in inches of the New Orleans Saints roster, okay? So bivariate data, weight versus height. And the landline telephones in the U.S., I'd be surprised if anyone has landlines still, but they could. It's number of landlines and then years since 2000. So there's two variables at play here that create this graph. So bivariate data. A scatter plot is a graph of the data, basically, that consists of ordered pairs on a common or on a coordinate plane. Okay, so the scatter plot, if you look down just below, you can see all the scatter plots there. Those are examples of scatter plots. And so, I think you guys have dealt with scatter plots in other classes before. Correlation, a term that is used to describe the trend of the data. Okay, so there's two ways you can determine the correlation. It can be positive and negative, but it can also have a number value with it. And I believe tomorrow we'll get into the number value. So if you look here, what I ended up doing or drawing was the line of fit. They call line of fit, line of best fit. And so as you see the consistency of the data points here kind of going in a positive direction, as it increases down the line, it gets higher. That is going to be a positive correlation. Likewise, if you see the consistency of data points here, they're getting smaller as it goes down the line, and so as a result, we have a negative correlation. Now, if all the data points are just spewed all over the page, they're just strewn over there in any random order, you have a no correlation, okay? And so I think this first one, as far as the New Orleans Saints are concerned, it has a general flow in this direction right here, okay? Now, it's kind of hard because it's getting wider, and the wider it gets, the less strong the correlation is, okay? Where the landline, the reduction in landlines over time, okay? Now, you might be asking yourself, what is a landline? I should probably tell you. It's the telephone that's connected to the wall. It's not your cell phone, okay? And so, as a result, when I grew up, there was landlines. In fact, I was actually on a party line in my neighborhood. I lived out in the country growing up, and I could get on the telephone, and there could be a neighbor speaking on the phone, and you'd be like, you had to wait till they were done to make your own phone call. And so, that's times have changed. So, anyways, landline telephones. Now, in moving on through the rest of the information I wanted to give you today, we have the line of fit. If you've ever heard of the line of best fit, that's where we're heading tomorrow. But the line of fit is this, a line that is used to describe the trend of data in the scatter plots. So as I kind of sketched out my line of fit down here for these correlations, the line of fit is that line that describes basically all the data points together, okay? Linear extrapolation, okay, versus linear interpolation. These are two terms that I've always heard, but I don't know if I ever really knew the definition of before. Extrapolation means to use the linear equation to predict values that are outside, so they're extra points. They're outside the data of the range of data. So extrapolation versus interpolation is kind of inside. And so maybe I should just do this. underline outside, underline the word inside right there, to use linear equations to predict the values that are inside the range of data, okay? So in this set of data right here, down at the bottom of the page, what I'm looking at would be, if it was extrapolation, it would be out here or down here. It's outside the data points, but if it's interpolation, it's somewhere in between the points there, okay? So here's what the problem says. The data shows the amount of milk that a baby goat needs by its weight. Use the data to determine the line of fit. Then determine how many ounces of 17-pound goat, ounces a 17-pound goat and a 55-pound goat would require, okay? Now before we get going any further, 17-pound goat would be somewhere right in here, okay? And so I'm thinking that is an interpolation versus 55-pound goat, which would be, I believe, right here, which is outside that data. So again, just trying to reinforce the understanding of interpolation versus extrapolation. So here's what I did. I went ahead and drew a line over here to the best of my ability that I felt like would represent all these data points, okay? Then from there, I identified 2 points that I thought were on that line. This one right here, which is over 5 and up 10, okay? So 5, 10 was my one data point. And the other data point was this one right here, which is at 30, 50, okay? So I did those 2 points and said, hey, I'm going to use those to find the equation of my line of fit. So I started with the slope here, 50 minus 10, 30 minus 5, and I got that fraction, reduced it down 8/5, dividing both those by 5, okay? Now from here I use that 8/5 with what looks like the smaller of the 2 points, 5, 10, okay? And then I, like we've done in the past, distribute the 8/5 through the parentheses, got my equation, and then added 10 to both sides. And this right here would be the equation of my line of best fit. Now technically, as I think about that, we could have left it just like this. This would have been fine right here. But force of habit, I almost always put it right back into slope-intercept form. Now how do we figure out how much milk a 17-pound goat is needed? Well, if you plug it in for X, okay, because this is the pound of the goat, right? Oh, if I can go down a little further. This is the pound of the goat, okay? This is the number of ounces of milk, and so I'm going to plug it in for X, the pound of the goat, and I'm going to go ahead and solve for Y to figure out how many pounds of milk it's going to need. So 29.2 pounds of milk per day, I believe, is what they needs by its weight. Yeah, I think it's per day. Which, you know, it isn't a ton of milk, to be honest with you. 55 ounces or pounds for the goat. I plugged in 55 for the X again, and I went ahead and solved for Y, and this time it's going to be 90 ounces of milk, okay, which is quite a bit more, about 3 times more. So anyways, I hope that makes sense. You know, use the 2 points in your line of fit to figure out the equation on that line. Yeah, go ahead and give those problems from page 311, 2, 4, and then 5 to 10 a go, and let me know tomorrow how you did. So thanks for listening. Good night.